Welcome everyone to a discussion with Claudio Paganini regarding his recent paper No Event on Closed Causal Curves. I hope you enjoy our discussion.
The motivation for me for writing this paper, so it was mostly really due to sort of as an advertisement for Fröhlich's ETH approach, or more actually for the mathematical relativity problem that comes from it, or that comes from this conjecture I introduce in the paper, which I call the causal compatibility conjecture. And basically, if you look at the result itself on a technical level, it's like once you assume this conjecture and you have all of Fröhlich's setup, then the result itself is actually, I mean, it's not entirely trivial, but it's pretty straightforward. So this is really not, like in itself is not a very technical paper from my point of view. But I wanted to have that conjecture written down somewhere to like being able to engage other people and go out to people and be like, hey, here's an interesting conjecture that is actually hard to crack, but it's interesting mathematically. And so like to get other people interested in the topic.
Right. So we have two components to this, right? We have the ETH approach, which is sort of, the approach that we're taking, and then we have this conjecture. I would like to talk about both of those. I don't know which one you find most natural to start with. Maybe we go over the ETH approach first, or...
Yeah, I think we'd have to start with that. So
okay. Would you mind just giving a high-level overview of what that means and how it's different from other interpretations?
Yeah, okay. So best is maybe to start sort of with the Copenhagen interpretation to quantum physics. That sort of is the best known interpretation of quantum physics. So if you have a physical system, basically it evolves unitarily in time unless you observe it. And if you want to observe it, you pick an observable, which mathematically corresponds to a self-adjoint operator. And then basically when you observe it, the measurement outcome will be one of the eigenvalues of that self-adjoint operator. And the probability for that outcome is given by the state. So you're essentially calculating the probability for certain eigenvalues, and that's giving you the likelihood of finding a certain value in your measurement device. Now, the issue there is that, and the important point that I was missing, I almost forgot. After you measure it and a certain value comes out, a certain eigenvalue, then actually the state projects onto the eigenspace of that eigenvalue. So now we are left with this situation where basically the physical system evolves according to one rule when we don't look at it. And as soon as we observe it, it follows a different rule. So this leads to all sorts of paradoxes, right? Because somehow then the question is, okay, like, what is an observer? So who can make these decisions? Like, why does me sort of like making a decision change the physical world? And this is very unsatisfactory. And this is, this is usually referred to as sort of like, or like that, like in various incarnations is referred to as the measurement problem. So that is somehow, it's unclear where to make the Heisenberg cut, which is exactly this sort of like, okay, when you have your laboratory, what is the probe and what is the observer? So like, is your vacuum chamber part of the probe or is it part of the observer? So where do you make the cut?
How do you approach that right now?
So here the thing is, I mean, that's not really my approach, but it's essentially in a paper by Fröhlich and Pizzo. They applied the ETH approach to answer that question more or less rigorously. But I think we have to put that a little bit back and first start sort of with the basic ideas of the ETH approach to then
Yes.
explain how to make that cut, because I think
Sure.
this is actually quite it's conceptually actually quite nice. So okay, so now we said in the Copenhagen approach, you somehow the observer has the choice to pick the observable and to pick the time of observation. Now here, the ETH approach does away with that. And basically, it gives you a formalism with which to determine a uniquely defined self-adjoint operator, and and basically what it is saying is, whenever you have such an operator and there are two different eigenvalues, so there are two possibilities that are mutually exclusive, meaning their projections are the projection operators are orthogonal and they commute, then nature chooses. So basically, whenever nature has a choice, it chooses. And now the thing is, a lot of the paradoxes already go away simply by the fact that you have a uniquely defined self-adjoint operator with respect to which this happens. So you cannot, it's not on to you to like say, oh, I pick this operator that I want to observe, but nature essentially picks an operator for you. Now, the thing is, whenever you have that situation that you have these two possibilities, at least two possibilities, then this projection, so then you have a projection. This is what Fröhlich defines as the event. So you have an event happening. Whenever an event is something that happens naturally, but you can roughly think of it, you can essentially think of it as a natural observation in the framework of the Copenhagen interpretation. But so you have this observation that is, but nature fixes you when it happens and with respect to which operator it happens.
Okay. So would this be applicable to, like, let's say we're talking about the double slit experiment or something like that. Is there a way to formalize that problem in the ETH approach such that our measurement of photons going through the double slits somehow fall into the category of a natural collapse, like as an event described by ETH? Or is it tricky to do that?
No, I think I think this basically I have to now go back to that Fröhlich and Pizzo result. So one of the central aspects or the important points about the ETH approach is that it's fundamentally based in the idea of open quantum systems. So you lose access to information as you progress in time. If, on the other hand, you would have a closed quantum system, then you would have no events happening in that system, so you would have no projections. Now, the thing is, what they did in their paper is basically they looked at the non-relativistic limit, and they coupled the local quantum system to a mock electromagnetic field. So basically what they said is like, okay, we have this local quantum system and it evolves in time, and we have this mock electromagnetic field through which we lose information. So basically whatever radiates away, that information you will never catch up with anymore. So this information is completely lost to you. And this is actually at the heart of like this loss of access to information, as he used to call it, or now like he refers to it as the principle of diminishing potentialities. That is at the heart of what makes the mechanism tick. So what they showed was basically if your local quantum system is weakly coupled to the electromagnetic field, then it evolves approximately unitarily. On the other hand, if it's strongly coupled, it evolves stochastically.
Okay.
And now the thing is, you can just add in a second system that you call the laboratory system. And now you say, okay, well, my laboratory system, or like, I mean, it emits thermal radiation. So it is naturally like all my lab equipment is sort of like strongly coupled to the electromagnetic field. But I have my probe. And my probe is isolated from the electromagnetic field. So basically what this is saying is like, well, so my probe will evolve unitarily, except for the moment when it interacts with my measuring device, because my measuring device is coupled strongly to the radiation field, and therefore, so the events affect the measuring device continuously. So you have a stochastic evolution for the measuring device. And as soon as your probe strongly interacts with your measuring device, then it, by the coupling of the measuring device, it also couples strongly to the electromagnetic radiation, and therefore the evolution of the probe also becomes stochastic. So this means you get an event that affects your probe. So basically, the way I summarize this in the paper actually is a laboratory experiment is a physical system that produces events in a predictable manner. And now we get to the double slit experiment that you were asking for. So one of the crucial insights from Fröhlich's approach is that as a physicist, you can only ever record events that happened. So the only question you're allowed to ask regard events. So, for example, in the double slit experiment, if there is no event that corresponds to left slit or right slit, then it's not a valid question to ask whether your particle went through the left slit or the right slit. But you can only ask, where did my particle hit the screen? So once you have your screen in the back and your particle interacts and there is an event happening related to your probe, then you can ask, where did that event take place? And you can make predictions about where these events will happen. But you cannot, if you do not engineer your experiment to generate events that correspond to left slit or right slit, then you cannot ask that question. So, I mean, I find this a very neat way of looking at it. And I mean, maybe just because I mentioned it quite in passing, but one of the key points I made there is you get a very operational definition of the Heisenberg cut.
Yes.
Essentially, it's any system that is strongly coupled to the electromagnetic field can serve as an observer. And so in the lab setting in particular, everything that emits thermal radiation.
Right. Is there a way to extend the formalism also to closed systems, or are open systems the only ones that are like, so what is it that breaks down for closed systems? We said before that, let's say information loss is at the heart of this theory. So the theory is inapplicable to other systems, or is it simply that this way of looking at, like, does the theory have another explanation for systems that are closed, or is it simply saying we only treat open systems?
Well, so I mean, this is essentially where like the argument in the paper comes in. Basically, if you have a closed system, then you have no event. So nothing happens. I mean, that's
Right.
it. That's and then of course what I show in the paper is that under a certain assumption, you can actually show that in chronology violating regions, so that means in if you have a background space-time that features closed causal curves, then in these regions you cannot have any events. So basically, it is sort of like in these regions, the physical system acts like a closed system, and nothing happens, and therefore, basically, from a physical point of view, this region is completely irrelevant because you cannot say anything about it. So
Okay.
that is essentially at the heart of the result is exactly this thing that if you have a closed systems, you have no loss of access to information, so you cannot have any event.
And if we're being a bit more rigorous on what an event actually means, so we talked a bit about how an event actually occurs now, but in terms of what it represents in the theory, is it equivalent to a standard measurement as we're used to thinking about it in, let's say, the Copenhagen interpretation or something like that? That you have a collapsing state onto the spaces of your eigenvalues in either in the operators, I guess.
Yes.
Okay.
Yes. I mean, this is what I said. So you you have this way for the theory to select this operator. So in particular, or actually equivalently speaking, it selects a family of orthogonal projections. And then basically when an event happens, so if two of them have a non-zero probability and they have different eigenvalues, then an event happens and you project onto one of them with the probability according to the probability, and then the state is updated with the collapse postulate. So you do have, so it's like in some sense it's a very conservative modification or completion of the theory, because it basically just takes what has been there sort of as like haphazardly like chunked together and integrates it into a framework that gives you unique answers, or like eliminates all the paradoxes by forcing your hand on certain aspects, like the choice of this observable or like of this self-adjoint operator.
And so does it conceptually make any sense to think about it as if the role that an observer played, originally speaking, is now played by loss of information in general in your system? That it's when your state interacts with something that extracts information from the system in some way, that causes a collapse? Is that kind of how you would reformalize the theory? Because in the Copenhagen interpretation, it's quite clear, right? You have an observer. It's unclear what that means, like to have an observer. But let's say you have that, and then that interacts with the system. It's a very clear definition of, or very clear intuition of what it means to collapse the state, or when a collapse occurs. And we're saying now that it interacts with the electromagnetic field, but what we're really saying, or my question is, if we are really saying that the thing that collapses the system is when it interacts with something that sort of carries with it loss of information. Because up until it interacts with that, the way I see it is it's kind of like you have a closed system up until that point, right? Up until it interacts with the electromagnetic field.
So I think I have to go a little bit more in the technicalities there, because I mean I think roughly speaking, your intuition is not entirely wrong.
That's something.
But so basically the thing is, you look at the whole approach, maybe to one step back,
Yeah.
is formulated in the Heisenberg picture. So you have the Schrödinger picture for quantum physics and the Heisenberg picture. In the Schrödinger picture, you have your observable is a fixed operator and your state, so the wave function evolves.
Yeah.
But this can be reframed. You can take a fixed state or a density matrix, and you can put the evolution into the operators. So here the whole picture here is very strongly based on that on the Heisenberg picture. And now the idea is basically when you have a point in space-time, you look at the future algebra that is generated. So that means the algebra generated by all physical potentialities that lie in the future light cone of that point. Now the point is, if you look at the point in the future, then that light cone is strictly embedded in that light cone. So what you say is like the future algebra of this future point is strictly smaller than the algebra of this point. And now the point is, why is this important? Well, for an event to happen at between these 2 points, you need that the commutator of the future algebra of the future point with the algebra with the future algebra here is non-empty. So you have to have something you have to have an operator that is supported between the 2 points and that commutes with everything in the future light cone. This is essentially when, like, from a practical point of view, if you only measure such operators that commute with everything in the future, then obviously that has no problems. So then all these sort of problems go away that you have with, well, if I measure that and then I measure that, but they don't commute, then you get weird sort of results. But so now we have, like, okay, now we have established, okay, somehow we have to have the algebras have to be contained in each other. Now, if I have an event happening at this point, so I project, then obviously this new state will not satisfy the condition for an event happening in the future of this point, because now this new state only has a non-zero, well, expectation value 1 with respect to all to a single projection, to a single eigenvalue of that potential observable with respect to that point. But now the point is, if you start with a pure state and you restrict the algebra, generally you get a mixed state on the future algebra. So this restriction of the algebra turns a pure state into a mixed state again. So, well, I mean, sort of speaking. And then, of course, that allows you to sort of restart, that you can get the next event and the next event and the next event, because you're always, you keep restricting your algebras as you move on forward.
How does the restriction of the algebra alter this state? Is there some intuition for that?
I mean, this is just if you have a pure state on a whole algebra. If you look at on a subalgebra, it's in general just not pure. I mean, this is like this is some algebraic result that I'm not 100% familiar with, I have to admit at this point. So yeah. Okay,
fine. But sorry for the interruption. I'll let you get back to it.
Well, but I mean, this is more or less I think what I wanted to say, because now now that we have this, so the loss of access to information is so this is so Fröhlich now refers to all these future potentialities. So obviously they get restricted. So you get this principle of diminishing potentialities. So an open quantum system, you have this. As soon as you close the quantum system, then that means your algebra is going to stay the same for all time. And so once your state is pure on that algebra, and well, then your algebra is not changing, then you will not have any events happening.
Okay.
That is, does that make sense?
Well, it kind of makes sense. I'm not sure how to tie it. I'm not sure how to tie it to the result of the paper. So maybe we can paint some more picture of how the two relate. So we're talking about closed causal curves in the paper. And does it relate to what you just described? I mean, it does on some level, but does it directly relate to it? And if so, could you please try to make that connection a bit more clear?
Yeah. Okay. So as I said, so one thing I have to now make is, so what I said so far implicitly assumed a semi-classical setup, because I was talking about light cones and future structures and whatnot, right? Now, a priori, Fröhlich's relativistic formulation of quantum theory works completely without classical spacetime. So you don't have to assume anything. You have an abstract space of potential. You have an abstract space-time of potential events with future algebras, and then you have a state, and so on and so forth. However, it is quite unclear, to me at least, how you would, like, at the end of the day, you somehow want to relate it to something we know and love with which we can calculate. So you want to have a space-time, and you somehow want to have fields on that. And as far as I'm aware, at the current time, it's completely unclear how to do that, how to get there from the abstract formulation. But what you can do, of course, is you look at the semi-classical setup. So that means you take a fixed background space-time, you put quantum fields on it, and you look how they behave. So in particular, it allows you, like in this semi-classical setup, you can associate observables to space-time regions in the algebraic approach to quantum field theory. And so what you can then do is just so I then introduce basically this causal compatibility conjecture, which is sort of really at the heart. I mean, it defines away the problem, basically. So
maybe I can pull it up as well.
Okay. That can if you record it on the paper, that's
yes,
probably,
I think it's this one, right?
Yeah, exactly.
Conjecture one.
So basically, what I'm saying there is, well, the future algebra associated with any 2 points. So here, j plus of x is the causal future of a point x. That means so this is classic relativity. So that means the j plus of x is, if I take a point x, then every point that can be connected to x with a future pointed causal curve, that means a curve that's everywhere time-like or null, is in the future of x. And so in particular, it's the future light cone emanating from x.
Right.
And so basically what this conjecture here is saying is just, well, there has to be a way such to define future algebras to regions such that if if x is in the future of y, then the algebra associated to x, to the future of x, has to be contained within the algebra associated to y. Huh?
Mm-hmm.
So this is basically saying that the causal structure of space-time is compatible with the definition of a causal order according to Fröhlich's ETH approach.
Mm-hmm.
And now the whole clue basically of the following argument then is just, well, if I have a closed causal curve, that means I have a point, I have a future pointed timeline curve that emanates from this point and that comes back to this point, huh?
Mm-hmm.
And so in particular, if I take any 2 points, then x and y that are on a closed causal curve, then y is in the future of x, but also x is in the future of y. And so then what you get is that, well, if you assume this causal compatibility conjecture, the only way this can happen is if the future algebra of x is the same as the future algebra of y. Because otherwise, if one of them were smaller, then you could not satisfy this condition. And so now this is basically saying that, well, within the causality violating region, that means the region where closed causal curves exist, your semi-classical system essentially behaves like a closed quantum system. And so there are no events happening in this region.
Okay, I'm just trying to wrap my head around the geometry, if there is any, in the way you would think about this. Like, we were talking about like cones, and you have a point, and then you have a curve residing from that point, and you want to see if you can have closed curves of that form. And then we're saying,
yeah,
please go ahead.
Sorry. So what I'm saying is I assume, for the sake of the argument, that I do have closed causal curves. So let's assume my underlying space-time is pathological in that sense that it allows for time travel.
Okay.
And now what I'm saying is, if this happens, and we assume the causal compatibility conjecture to hold, then actually within this causality violating region, our physical, like the semi-classical setup, will be a closed quantum system. So the algebras will be constant along the curve, and the states will be the same. So we have no projection, so we have no events happening in that region. So,
and how come? Does it make sense? So, what is the connection between a closed causal curve and an event? So we're saying. So I buy what you're saying. We don't have any events taking place, but we nevertheless could, from my perspective, as I see it, draw a curve. Right? That's a closed causal curve in that spacetime. What is the necessity for, or what is the connection between the events and this curve that we're now trying to draw?
So as I was sort of explaining before with the double slit experiment, as long as no events happen, you can only answer questions, like you can only ask questions of the physical system of events. So now the thing is, essentially when I have my space-time, a priori, there could be events happening all over the place. In principle, at every space-time point, if I have this conjecture, you can have every space-time point has a possibility of corresponding to an event.
Yes, fine.
Now the thing is, what I show, and then of course, if you are on a closed causal curve and things happen there, then you get into all these paradoxes, right? You go back in time, you kill your grandfather, and then, but if your grandfather dies before you're born, before your father is born, then you're never born, so you cannot go back in time, and so on and so forth.
Right.
However, all of the things I just said are events, right?
Mm-hmm.
I mean, you have to kill your grandfather, that's an event. Your father
Well, I
is
mean,
born.
this is a this is a very particular example, no? Like, yes, these are all events, but nevertheless, like, you could make the case that if you don't have, so is the case you're making that if you have something that would be able to create a closed causal curve, then, and you're not allowed to have events on that, then it doesn't matter whether or not you can create the technical construct. The only thing that matters from the perspective of a measurable universe, let's say, is if it allows for events to take place. Is that the connection that I was lacking before?
Yeah, exactly.
Okay.
That's precisely the point that I'm making. So even if you like, I mean, in this semi-classical setup, you start with a fixed spacetime background, right? And so I can give it all the pathologies I want. For example, closed causal curves. But
Right.
now what I'm saying is, well, if I give it this pathology, quantum theory will get rid of it because simply nothing will happen in there. So you cannot ask any questions about it.
Mm-hmm.
So, yeah, you cannot kill your grandfather. You cannot be born on a closed causal curve. All of this doesn't happen because there's no events happening there.
Right. Okay. And what is then the underpinning argument for the conjecture? So you list a few of those, I think, in the paper somewhere around here as well. But would you mind elaborating a bit on what motivates the conjecture in the first place?
Yeah. So I mean, this is this is a really subtle mathematical problem. It's sort of funny. Like I've now been shopping the problem around for a bit, and many people that I talk to have an initially very strong opinion. So either, yeah, this is clear, or no, this is clearly wrong. But then as soon as I sort of like give them arguments in the other way, they realize like, oh no, it's actually a very subtle problem. So here's the deal to it. If you look at simplest case, massless scalar wave equation. So you have a scalar field that satisfies the massless wave equation, and you are in Minkowski space, and you have 2 points. So you have a point y and a point x in the future of it. So you can look at what is called the causal diamond. So that means the intersection of the past of x with the future of y. So that is sort of like this region of space-time that's called the causal diamond between the 2 points. Now, if we take the causal Green's function and we take a source function that is supported only in that causal diamond, then in Minkowski space, what we know is that the solution will become zero in the future light cone of the future tip of the causal diamond. So in particular, that means if we go to operators, any operator that is supported in the causal diamond will commute with any operator that is purely supported in the future light cone of the tip of the causal diamond. So basically, in Minkowski space, the causal compatibility conjecture is known to be true, thanks to Huygens principle. Now, as soon as you introduce curvature, the statement is not true anymore in general, because you have what is known to as backscattering. So you will not have like the solution will only like generic solutions when you take a fixed spatial region and you look at in time, then the amount of energy that's in that region will generically only fall off with like a polynomial tail. Or if you're in an expanding universe, maybe an exponential tail. But nevertheless, it doesn't go to zero. It doesn't drop sharply to zero. In flat space, it drops to zero. And now, of course, there is the question, well, okay, for a generic solution, that is true. But can we maybe, so for the causal compatibility conjecture to be correct, it is actually sufficient if you have a single solution that satisfies this property. So in Minkowski space, it's for all solutions that have their source function supported in the causal diamond. This thing is true. But that's not what we need. What we need is a single function satisfying this property. And that is a subtle question because, so, for example, it's very easy to construct a solution that is zero in the future of a point. Namely, the way you do that is you take the future of the point, and then basically you solve the backwards problem. So the future lifetime of this point will intersect null infinity. So this is explain null infinity is sort of tricky, I guess. But anyway, let's just for the sake of let's see. So there is something out there that is called null infinity, and in principle you can look at the backwards problem. And so if you put the initial data on the future light cone to zero, then obviously, so you can, if you solve the characteristic initial value problem to the future, the solution will be zero. And if you solve it to the past and you put non-trivial data on the boundary, then you will get a solution. Now, the issue there is that if you look at that solution and you take a generic Cauchy surface, so a space-like surface that slices through your entire space-time, then it is absolutely not clear that these solutions will be spatially compact in support. So that means now the problem is, if I can build this solution, but now for this solution I don't know whether, if I look at any point in time, the solution will be zero outside of a compact region. So this is one way to look at it. And then the other one is, and of course, it's very easy to, spatially compact solutions are plenty. So any solution that we generate from a compactly supported source function will be spatially compact. So you get one property or the other property, relatively easy. It's not clear that you can get both properties at the same time.
Okay.
And yeah, I mean, there's one other argument that you can do is like these beam approximations. So this is based on a result by Spearsky, who basically showed that, well, if you have a null geodesic, and you have a solution to the massless wave equation, then you can find a solution that is arbitrarily well focused along that null geodesic. So that means, like, if I give you any epsilon and I say I want all the energy of that beam, of that solution, all but epsilon of the energy to stay within the tubular neighborhood, so like within a small neighborhood of this null geodesic, then you will be able to find such a solution. So in particular, of course, when I have two light cones, I can pick any null geodesic that is in between them and it goes out to infinity. And what this result tells me is that, well, I can pick a solution that is like for an arbitrarily small epsilon, I
Yeah.
will always find a solution that goes out that has everything but that epsilon in between, like sandwiched in between these two light cones.
Yeah.
And well, epsilon is probably not good enough. So the question is, can you get zero?
Uh-huh.
Yeah.
Okay. Okay. In terms of making heads or tails out of this,
Yeah.
is there a way to approach it? Is there a way to make like? Do you think there's a way to make headway here? What would be the next steps for this?
I think the easiest or the clearest thing to do would be to actually start like doing some calculations in Schwarzschild, because I mean there's several reasons for that. Basically black hole spacetimes already have all the issues, so you have backscattering.
Uh-huh.
But on the other hand, you do have a high degree of symmetry, which makes the equations manageable. And of course, if it would
Why
fail,
is that? What kind of symmetry are we talking about then? And why does
spherical
that make them?
symmetry and
Okay.
stationary. I mean, I
Uh-huh.
mean, Schwarzschild black holes are spherically symmetric and stationary, so they're basically only changing in radial direction. So you only have one. You only have one coordinate that's really doing something weird, so to speak.
Right. Uh-huh.
Um, so yeah, I mean that would be clearly like the first toy example, and it has also the advantage. So there has been this whole I don't know whether you've heard of that, like the whole chase for black hole stability. So this is like trying to prove that if you poke a black hole, it will settle back down to a black hole in reasonable time. And what this has done is this has been an enormous mathematical effort of a
Uh-huh.
rather big community. And so there have been developed a lot of tools that are specifically like developed in the context of black hole spacetimes, and Schwarzschild as the simplest example. And so these two sort of things would be like or like these two arguments would sort of be the reason why you'd want to start there. So
Uh-huh.
you have a big mathematical toolbox. You have a clear space-time, and it's non-trivial.
Okay.
So, I mean, maybe to like one thing I forgot to say, of course, is that all the space-times that are conformal to Minkowski space, that means in particular FRLW, so Friedman, Robertson, Lemaitre, Walker, they automatically satisfy Huygens principle. So this principle also holds in these spacetimes. So in principle, you could say like, oh, okay, well, on a universal scale, it holds. So what do we care? But I think that's like from a mathematical point of view, it's mostly like it's a very interesting mathematical problem. So I yeah, I am keen, but it's a hard problem. I think it's a really hard problem.
Okay. In terms of wrapping up the paper or concluding,
Yeah.
because we only have a few minutes left, is there anything you would like to highlight with it that we didn't touch upon yet? Any like results or any additional points that are worth noting for the audience?
Well, I think we touched on most of it already. I think it's like really Fröhlich's approach is really interesting, I find, because it's a consistent, complete formulation of quantum theory that gets rid of many paradoxes.
Yeah.
It gives a natural a natural definition of the Heisenberg cut, so to speak. And yeah, I think it gives interesting mathematical problems. to work with. So I think this is basically like the main thing I wanted to say with this paper, with an emphasis on the last one, that there's actually something really interesting happening mathematically, or like a really challenging problem that could be solvable, but it's unclear with current technology,
Okay.
current
Awesome.
mathematical technology.
Yes. Cool. I'm happy to wrap it up here then. Thanks
Okay.
a lot for taking the time to explain it. Enjoyed it very
Yeah.
much.
Thanks for the interest,